In this problem, we have a semicircle of radius a with positive charge on the left-hand side on the left half and negative charge on the right half of the semicircle, and we'd like to calculate the electric field vector at the origin. First, I'm going to calculate the electric field vector due to negative charge distribution. Then I'll calculate the electric field due to positive charge distribution and add the two electric field vectors together. Because this is a two-dimensional problem, each electric field vector will have an x component and a y component that we will calculate separately. We start by dividing our charge distribution into small pieces that will act like point charges, and we call those pieces dq. So here's one of those pieces dq in the picture, and the point charge dq is creating an electric field vector dE pointing towards itself from the origin. Now in this problem, it is convenient to use theta as our integration variable because the position for each dq can be easily expressed using theta. Also, the components of dE will depend on theta, right? As theta goes from 0 to 90 degrees, the x component of the electric field will get smaller and the y component will get larger. So the components depend on theta, and the position of each point dq can be expressed in terms of theta. We choose theta as our integration variable. Now I'm going to call this electric field vector dE minus, and the components of dE minus sub x, dE minus sub y are as shown in the picture. So let's go ahead and express these components, starting with the x component. X component of dE is going to be equal to dE times cosine theta. Again, this is negative dE, so I have a negative sign here to indicate that we're working on the negative charge distribution. So now let's go ahead and express dE using the formula for electric field due to a point charge, because this dE is created by the point charge dQ. Applying the point charge formula, dE minus is equal to dQ divided by 4 pi epsilon 0 a squared, a being the distance from dQ to the origin. Now the next step is to express dQ in terms of d theta, our integration variable, so we can actually take this integral. For that, let's introduce the linear charge density lambda. Lambda is defined as total charge divided by the length of this charge distribution. Now the total charge is capital Q. The length is a quarter of the circumference of the circle. The circumference will be 2 pi a. 1/4 of that is 2 pi over 2, so times a. Rearranging the equation, I get lambda equals 2 times q divided by pi times a. Now you may have noticed that I'm not using negative q anywhere. That's because the negativeness of the charge allows me to determine the direction of the electric field. So I know that the electric field vector lives in the first quadrant because the charge is negative, and I have already used that information, so I'm no longer substituting any negative charge in my calculations. So I'm going to use the same charge distribution for the positive q half of the semicircle as well. Now lambda is also the charge density of the unit element dq, right? So it's equal to dq, the charge on the unit element, divided by the width of the unit element, which we can express as a times d theta. Now let's see with a larger picture why the width is equal to a times d theta. The angle that is subtended by dq is simply d theta, and the width of dq is really just this arc length here. Using the arc length formula, this width, this green segment, this green arc length, is equal to a times d theta, a being the radius of the circle that completes this section, and d theta is just the angle corresponding to the arc length. So then this green segment is really a times d theta. We multiply the radius by the subtended angle. Going back to our calculations, we combine these two equations to eliminate lambda, and we isolate dq. Now we have dq expressed in terms of the given variables and d theta. Note that I introduced the intermediate variable lambda and then I made it disappear because it's not a given variable in the problem. Next, we go back to our integral and substitute for dq the expression that we just found involving d theta. And here's our integral expressed in terms of our integration variable theta. So it can be simplified a little bit, and I'm going to also pull out the constants. Also at this point, because our integral is now in terms of the integration variable, we can put the lower and upper bounds. So theta will run from 0 to pi over 2. And here's our integral with constants pulled out of the integration and simplified. Now this is integral of cosine theta d theta, which is simply equal to sine theta. Here I took care of the integration, and in the next step, let's go ahead and evaluate our integral from 0 to pi over 2. Sine pi over 2 is equal to 1, and sine 0 is equal to 0, so this integral part is simply equal to 1 minus 0, which is 1. So then here's our final answer. X component of the electric field due to negative charge distribution is equal to capital Q divided by 2 pi squared epsilon 0 a squared. Now let's go ahead and find the Y component following a very similar method. So the Y component of the electric field is basically the integral of the Y component of dE, and the Y component of dE is dE times sine theta instead of cosine theta. So the expression here is going to be extremely similar to the previous one. So we'll have to go through the same steps with sine theta instead of cosine theta. Up to this point, everything is identical except that instead of cosine theta, we're going to have sine theta. So let's go ahead and write this down. Here's our integral for the Y component. It's identical to the one with the X component, except instead of cosine theta, we have sine theta. Now we're going to integrate sine theta over d theta. The integral of sine theta is negative cosine theta. From here we get minus parentheses cosine pi over 2, that's 0, minus cosine 0, which is 1. So I have negative 1, so this is equal to positive 1. So the Y component is positive, which is what we expected. We expect the electric field vector to live in the first quadrant. So both the X and Y components are positive. Here's our final answer for the Y component of the electric field due to the negative charge distribution. You may have noticed that it's exactly the same as the X component. The two components have the same value, which makes sense because there is some symmetry around the 45-degree line. So the electric field vector due to negative charge is making an angle of 45 degrees with the positive x-axis, its x and y components being equal to one another. Now let's focus on the positive charge distribution. Again, we have our dq unit element that creates an electric field vector dE plus this time at the origin. Now the situation is extremely similar actually. We are going to integrate again over dE sub x and dE sub y for the positive electric field, positive charge distribution's electric field. The only difference is that the angle now spans, so here's my angle theta, right? Here's the angle theta. Now when I integrate dE when I integrate the expression over d theta, theta should go from 3 pi over 2 to 2 pi because the vector dE plus now is in the fourth quadrant. Those vectors, or the vectors dE, span the fourth quadrant. So theta runs from 3 pi over 2 to 2 pi. And again, the x component of dE is going to be equal to dE times cosine theta. The y component will be dE times sine theta. Note that sine theta in the fourth quadrant is negative, and that makes sense. I have a vector pointing with a negative y component pointing towards the lower right corner, so it has a positive x component, negative y component, and that matches the theta values in the fourth quadrant. Here I copied my result from the x component of the electric field due to negative charge distribution. The only thing I changed is the integral limits. So I have the lower bound set to 3 pi over 2 and upper bound set to 2 pi. What is this equal to? Sine 2 pi is equal to 0 minus sine of 3 pi over 2, which is equal to negative 1. So minus 1 is plus 1. So this is equal to just 1. So here's my result for the x component due to positive charge distribution. And it is equal to the x component due to the negative charge distribution. Now let's go ahead and calculate the y component of the electric field due to positive charge distribution. Again, I copied my result from above for the y component of the negative charge distribution. The only thing I changed is the integral upper and lower bounds. Now theta runs from 3 pi over 2 to 2 pi. Let's calculate this. This is equal to, so I have an overall sine of negative 1, and then cosine 2 pi, that's 1, minus cosine of 3 pi over 2 is 0. So from here I get an overall factor of minus 1. Here's our result for the y component of the electric field due to positive charge distribution. Again, it's the same expression, but this one is a negative component. Next, let's calculate the net electric field by adding the electric fields due to positive and negative charge distributions. To find E net, we will add E minus and E plus. So first, let's find the x component by adding the x components. These two components have the same value, so we're just adding the same thing twice. It's basically one of the components times 2. So combining the two terms, so here's E net x component. Let's find the y component of the net electric field vector. Now we add the y components together. The y components are equal and opposite, so they cancel out. So we get E net y equals 0. So the magnitude of the net electric field is equal to its x component, and its direction points in the positive x direction. Here's our final answer. Net electric field vector presented in terms of its magnitude and direction angle. Its magnitude is equal to capital Q divided by pi squared epsilon 0 a squared, and its direction angle is 0 degrees, meaning the vector is pointing in the positive x direction.